Imagine, for just a second, a multi-million-dollar AI factory.
Right.
We are talking about, row after row of the most advanced supercomputers on the planet,
Yeah.
just crunching through these massive large language models and consuming just megawatts of
Yeah,
power.
yeah, absolute power hogs.
Exactly.
Yeah.
But now imagine that facility isn't just plugging into the electrical grid like like a giant dumb appliance.
Right, which is how we usually think of them.
Yeah. Imagine it is actively playing the wholesale energy market, like the exact same way a Wall Street day trader would.
It is a complete inversion of how we normally think about infrastructure, really.
Exactly. Picture a system that can look at the fluctuating price of electricity, see like a massive spike coming because of a heat wave, and just automatically throttle thousands of high-end GPUs down to a crawl.
Right, to dial it back.
Yeah, the exact same way you would turn down a garden hose in your backyard.
Mhm.
Just slows the math down, saves a fortune, stabilizes the local power grid, and then boom, ramps right back up the millisecond the price drops.
It really is wild. The facility essentially transforms from a passive consumer of energy into a highly dynamic, active participant in the global power markets.
Yeah.
It is not just doing math anymore. It is actually balancing the electrical grid.
Which is just crazy to think about. So welcome to another deep dive. Today we are pulling back the curtain on the invisible architecture that is frankly running the modern world.
Absolutely.
We are looking at the convergence of three massive disciplines here. We've got extreme AI computing, sustainable liquid cooling, and dynamic grid-aware energy management.
Yeah, it's a massive intersection.
It is. And we are pulling all of this together for you from a really fascinating stack of internal demonstrations, architectural walkthroughs, and technical blueprints.
Right.
These span all the way up through the major announcements of 2026.
And what is particularly compelling about this material is the sheer granularity of it all.
Right.
We are looking at the actual blueprints of Supermicro's SuperCloud Composer, which admins usually just call SEC, by the way.
Okay, SEC.
Right. And their power grid manager, and the broader green IT initiatives that make this kind of insane density even possible in the first place.
So our mission today for you, the listener, is to decode this convergence. We're going to figure out exactly how these modern AI factories are kept from literally melting down under their own computational weight.
Because they absolutely would melt down.
Right. And then we're going to explore how that localized thermal management is secretly acting as the foundation for this wild integration with the global electrical grid.
It is just a phenomenal engineering journey, honestly, because you literally cannot have the macroeconomic grid integration without first solving the micro-level fluid dynamics on the actual microchips.
Wow, yeah.
The physics dictate the economics.
I love that. The physics dictate the economics.
Yeah.
Which, brings us right to the physical layer, the heat problem.
Right.
Anyone following the semiconductor industry knows that the thermal design power, the TDP of these chips, has been just skyrocketing lately.
It's off the charts.
We are way past the era where we have to explain that, hot things need fans. The audience knows that.
Yeah.
But the mandates that have come down from the giants, like AMD and NVIDIA, they represent a fundamental, non-negotiable physical threshold, don't they?
They really do. The mandate from them is unequivocal. Moving forward, high-end GPU accelerators will absolutely require liquid cooling.
Period.
Period. It is no longer an enterprise upsell or some bespoke configuration for a boutique research lab. It is a fundamental operational requirement for the silicon to even boot up without just destroying itself.
Wait, really? Just booting up?
Oh, yeah. When you are pushing, say, a kilowatt of power into a single piece of silicon, the heat flux, which is the amount of thermal energy concentrated in a few square centimeters, it is simply too dense for forced air to remove.
Because air, as a medium, just cannot carry that much energy away fast enough, right? Like, no matter how much static pressure you generate with a high-speed fan, you put a literal jet engine at the end of the server aisle, and the chicks in the middle of the rack would still thermally throttle.
Precisely. You have to realize the volumetric heat capacity of water is roughly 3,000 times greater than that of air at sea level.
3,000 times. Oh, wow.
Yeah, it's a massive difference. So if you want to maintain the clock speeds necessary for modern AI workloads, you have to transition to a medium that can absorb and transport extreme thermal loads instantaneously.
Right. And this is where Supermicro's Green IT initiative really caught my attention in the architectural walkthroughs. Because it's very easy to look at an NVIDIA mandate and assume the server manufacturers are just frantically bolting plumbing onto their existing chassis to keep up.
Right, like a Band-Aid fix.
Yeah, exactly.
Yeah.
But Supermicro CEO Charles Ling actually founded their Green IT initiative over 30 years ago.
And that historical continuity is a massive competitive advantage for them.
I bet.
When you look at their evolution, they didn't just wake up in 2023 and decide to learn fluid dynamics. They started with highly optimized sheet metal chassis and then moved into complex rack-scale airflow designs, and they have been iterating toward full, turnkey, liquid-cooled architectures for decades now.
Because transitioning a whole data center from air to liquid is just a logistical nightmare, isn't it?
Right.
It's not just swapping out a heatsink.
Oh, not at all. It requires a fundamental rethinking of the structural engineering of the building itself. You have to think about the weight-bearing capacity of the raised floors, municipal water supply, electrical routing. Having a 30-year runway to optimize those integration points is exactly why they are currently able to deploy at this massive scale.
So let's look at how this scale is actually managed. In the demonstrations of SuperCloud Composer specifically, they were looking at version 3.40. They show this interface called Pod View.
Right, Pod View.
And it is this graphical representation of the entire server rack. And the very primary identifier, like the first thing the DevOps admin sees to know they're looking at a next-generation setup, is just a simple water droplet icon sitting on top of the rack visualization.
It is a really brilliant piece of UI design.
Right.
Because it immediately establishes a completely new mental model for the administrator. That single droplet dictates everything about how that rack will be managed, serviced, and monitored from that point on.
And the physical reality of what that little droplet represents is staggering. The material details how these racks ship. They use this terminology. L10s and L11 services.
Yes.
And what that means is these racks ship as complete, fully pre-populated pallets.
Right, so let's pause and think about the logistics of an L11 delivery for a second. Historically, a data center would receive a rack, and then they'd receive hundreds of separate cardboard boxes containing servers, switches, cables, and power distribution units.
Just a sea of cardboard.
Exactly. And a team of technicians would spend weeks racking, stacking, cabling, and configuring every single component.
Which is incredibly labor-intensive. And, I mean, the margin for human error has to be huge. Someone bends a fiber optic cable too sharply, or they plug a server into the wrong PDU phase.
It happens all the time. But with L10 and L11 palletization, the entire rack, which is weighing upwards of 3,000 pounds, by the way, arrives fully assembled.
Wow.
The Ethernet switches for the management network are already wired. The InfiniBand connections for the high-speed data plane are perfectly routed.
And the PDUs, the power distribution units. The architecture specifically mentions supporting universal agents for PDUs from Schneider Electric,
Yep.
Elon, Eaton, and Servertech.
Right.
They aren't like locked into a single vendor. They can integrate with whatever high-voltage infrastructure the facility already uses, which seems huge.
And that is critical because these racks are pulling immense amounts of three-phase power. But honestly, the most terrifying part of shipping a pre-populated liquid-cooled rack is the fluid loop itself.
Oh, man, yeah.
Every single hose, every manifold, every quick disconnect fitting is already plumbed. They have to engineer these pallets to survive the vibration of a semi-truck traversing the country without compromising a single microseal in the fluid loop.
Just bouncing down the highway. That is terrifying. Which brings us to the heart of that fluid loop, the CDU, or Cooling Distribution Unit. The physical blueprints place this CDU at rack slot unit 1, which is the absolute bottom of the standard 12U rack setup.
And placing it at the bottom is a very deliberate choice driven by basic physics.
Gravity.
Exactly, gravity. In the event of a catastrophic failure, gravity ensures that escaping fluid travels downward, away from the expensive compute nodes above it. But operationally, the CDU is the mechanical heart of the entire rack.
Okay, let's unpack this mechanically. It pushes the fluid across what they call proprietary cold plates. We aren't just talking about a pipe running past a computer, are we? These cold plates are physically mounted directly onto the bare silicon of the CPUs and GPUs.
Yes. Think of the cold plate as a highly engineered thermal bridge. Inside that plate, there are thousands of microscopic copper channels, called microskeived fins.
Microskeived fins.
Right. The goal is to maximize the surface area that the water physically touches. The CDU pumps the chilled water through these microchannels. So as the silicon generates heat, that thermal energy transfers through the copper directly into the water. The now heated water is pushed out of the rack to a heat exchanger, cooled down, and recirculated back in.
And the density they are applying this to is just insane. The blueprints highlight a specific setup to demonstrate the capacity, and they are using 4U AMD EPYC servers. So for the listener, that's a server roughly 7 inches tall.
It's tiny.
Yeah. Inside that single chassis, you have dual AMD EPYC processors with 96 cores each, and crammed in right alongside them are 8 local NVIDIA H100 GPUs, each with 80 gigabytes of high bandwidth memory.
To put that in perspective, a single H100 GPU can draw 700 watts of power all by itself.
700 watts.
Yeah. When you put 8 of them in a single 4U chassis, plus the dual CPUs, the memory, the networking interface cards, you are essentially creating a localized furnace.
The technical readout specifies exactly how dense this is. Across the CPU nodes and accelerators, they cataloged 11,152 individual components installed in that tiny space.
It's mind-boggling.
1,152 heat-generating components in a box the size of a microwave.
This is exactly why the CDU and the fluid dynamics are so critical. If you have 1,152 components, the fluid loop has to be perfectly balanced.
Right.
Because if the water pressure drops significantly by the time it reaches the last GPU in the loop, that GPU will thermally throttle while the first one stays freezing cold.
Oh, I see.
So the CDU has to dynamically manage flow rates, static pressure, and pump redundancy to ensure perfectly even heat extraction across an impossibly dense landscape of silicon.
Okay, so you have this marvel of physical engineering. You have microscopic copper channels, perfectly balanced fluid pressure, thousands of pounds of silicon, and massive power draws.
Yep.
Which immediately raises a massive operational question for me. How does a single DevOps administrator, or even a team of them, manage this? If the physical layer is that complex, the telemetry data must be an absolute fire hose.
It is a phenomenal amount of data, and this is where we actually transition from the physical layer into the software layer.
Okay.
Because you can build the most robust cooling loop in the world, but if you cannot observe its state in real time, you do not have an enterprise-grade AI factory. You basically have a science experiment waiting to explode.
Right. And Supermicro's answer to this telemetry fire hose is SuperCloud Composer, the SEC. What struck me in the documentation was the sheer geographical scale of how this software operates.
Yeah, they really pushed the boundaries there.
In a live demonstration from 2023, they intentionally showcased SEC's global reach. They had the actual management appliance, the software hub running in Taipei, Taiwan, and it was pulling metadata in real time across the Pacific Ocean from a physical liquid-cooled rack operating in a data center in San Jose, California.
That demonstration really highlights the power of out-of-band management networks.
Out-of-band, what does that mean in this context?
It means the telemetry data, the pump speeds, fluid temperatures, fan RPMs, power draw, all of that is completely decoupled from the data plane.
Oh, I see.
So the server could be crunching a trillion parameter AI model, absolutely saturating its InfiniBand connections with math, but the SEC appliance in Taiwan is still maintaining perfect, uninterrupted visibility into the hardware state via a dedicated, low-bandwidth management channel.
That is wild. But I want to push back on this design philosophy for a second, because the documentation heavily promotes this concept of a single pane of glass UI.
Yes, the unified dashboard.
Right. The idea that everything, from the global fleet down to the individual water pump, is managed from one interface.
Yeah.
From a cybersecurity perspective, or even just an operational perspective, isn't a single pane of glass also a single point of failure?
It's a fair question.
I mean, if an attacker compromises SEC, don't they gain the ability to physically destroy the cooling infrastructure of an entire global fleet?
It is an excellent pushback, and honestly, it is the central tension of modern infrastructure management. Centralization brings immense efficiency, but it undeniably concentrates risk. However, the architectural defense against that risk is heavily emphasized in the SEC design, and it relies on strict, granular, role-based access control, or RBAC.
RBAC. Yeah, the documentation does detail how the UI aggressively filters what a user can see and do based on their assigned role.
Exactly. The single pane of glass is highly deceptive. It is not one static screen that everyone looks at. The interface actually physically morphs based on your cryptographic identity.
Oh, wow.
So if you log in as a data scientist, your pane of glass shows GPU utilization, memory allocation, and job queuing. You have zero visibility into and zero control over the CDU pump speeds or the PDU voltage states.
And if you are the network admin, you are looking at InfiniBand link states and packet loss, completely blind to the GPU inference tasks.
Precisely. Only a top-tier facility administrator has the credentials to adjust the physical infrastructure parameters, and even then, those actions are heavily gated by policy engines and multi-factor authentication.
So they can't just click a button and turn the water off.
No. You mitigate the risk of the single pane of glass by ensuring that an attacker who phishes a data scientist's credentials cannot pivot and turn off the water supply to the rack.
Let's talk about the specific UI details, because they give a really great sense of how the software prioritizes information for those facility admins. They mention these subtle toast messages that pop up in the corner regarding trial license enforcements, keeping the admin aware of compliance with interrupting workflow.
Which is a nice touch.
Yeah, but the feature I found completely fascinating was in the liquid cooling console. It's this simple widget, a carousel view, that automatically scrolls every 5 seconds.
Ah, yes. It cycles back and forth between two specific metrics, correct?
Yes. Coolant return temperature and coolant supply temperature every 5 seconds. Supply temp, return temp, just endlessly looping. Why dedicate prime UI real estate to those two specific numbers?
Because the relationship between those two numbers represents the absolute heartbeat of the AI factory. We are talking about the thermodynamics of heat rejection. The coolant supply temperature is the water entering the rack, how cold the facility is delivering the fluid. The coolant return temperature is the water exiting the rack after it has absorbed all the heat from the silicon.
So the difference between them
is the delta T. The delta T is the ultimate macro metric.
Delta T.
Right. If your delta T is too small, it means the servers aren't doing any work or the fluid is moving so fast it isn't absorbing heat. If your delta T is massively wide, it means the servers are running red hot and you are extracting immense amounts of thermal energy.
Oh, I get it.
By forcing the administrator to constantly watch the supply and return temperatures toggle back and forth, the UI is intuitively training them to internalize the thermodynamic rhythm of the facility.
That is brilliant. And for the actual compute side, they have this highly customizable Grafana-style dashboard for GPU performance metrics. But the technical specs explicitly note that this dashboard pulls the hardware every 10 seconds.
Yes, 10 seconds.
Now, in the world of high-frequency trading, or, just fast computing, 10 seconds is an eternity. Why pull every 10 seconds? Why not every second or every millisecond if you want real-time visibility?
It is a highly calculated compromise between visibility and overhead. Every time you pull a BMC, baseboard management controller for a metric, you are using CPU cycles and network bandwidth.
Right.
If you have 11,152 components in a single rack, and you have 50 racks in a pod, and you pull every single component every 100 milliseconds, you will literally cause a distributed denial of service attack against your own management network.
You would literally crash the monitoring system with the monitoring data. That's hilarious.
Exactly. But if you go the other way and pull every 60 seconds, a water pump could fail, and an H100 GPU could completely cook itself before the dashboard ever updates.
Wow. Yeah.
So a 10-second polling cadence provides enough resolution to catch sudden thermal anomalies or computational spikes while keeping the management network traffic light enough to scale globally.
Here's a feature that truly blew my mind, because it perfectly illustrates the bridge between the physical and the digital. The walkthrough, details in the manifolds, the massive vertical pipes running down the side of the rack that distribute the fluid to the individual chassis.
Right.
They're color-coded, obviously, for supply and return. But if a human technician on the floor makes a physical mistake and somehow manages to plug a supply hose into a return manifold, literally plugging it in backward, the SEC software actively detects the physical reversal and throws an immediate alert.
That is a phenomenal piece of engineering.
Yeah.
And to understand why that matters, you have to think about the physical consequences of that mistake.
Which are bad, I assume.
Very bad. If you reverse the flow on a high-pressure liquid loop, you aren't just failing to cool a server, you are potentially deadheading a mechanical pump, fighting the internal check valves, and starving an entire cascade of $40,000 accelerators of their thermal rejection path.
But wait, how does software, sitting all the way in Taiwan, know that some guy in San Jose plugged a rubber hose in backward?
It relies on a matrix of differential pressure sensors and flow meters embedded at the manifold junction. The software knows what the pressure gradient should be.
Right.
If the supply sensor suddenly reads a negative flow rate or an inverse pressure drop relative to the return line, the software instantly deduces that the physical topology has been inverted.
It's not just monitoring, it's actively QAing the human technicians. That's incredible. So how does this level of telemetry, the global reach, the delta T tracking, the reverse hose detection, actually change the day-to-day existence of the infrastructure team?
It fundamentally shifts the entire operational paradigm from reactive to predictive. Historically, running a data center was a giant game of whack-a-mole.
Whack-a-mole, yeah.
You waited for a server to overheat, An alarm would scream, a ticket would be generated, and a technician would literally run down the hot aisle to see what broke. It is incredibly stressful, and by the time the alarm goes off, you have already suffered hardware degradation or workload downtime.
You are fighting fires after the house is already burning.
Exactly. But when you are synthesizing thousands of data points every 10 seconds into a time series database, you gain the superpower of trend analysis. The administrator isn't waiting for a failure. They are looking at the Grafana dashboard and noticing that the coolant return temperature on node 14 has crept up by 0.2 degrees every day for the last 12 days.
The server hasn't failed. It's not even throttling yet.
Right. No alarms are sounding. But the trend line proves that something is degrading. Maybe a microchannel in the cold plate is slowly clogging with particulate. Maybe a pump bearing is beginning to wear out.
So they see it coming.
The admin can see the failure coming a week before it happens. They gracefully migrate the AI workload off that specific node, schedule a maintenance window, swap the part, and return it to service with zero unplanned downtime.
And the architecture notes emphasize that SEC isn't just looking at the hardware in a vacuum either. It actively synthesizes physical asset, data like pulling the specific serial numbers of the GPUs or checking the firmware versions of the management controllers, and correlates that directly with environmental telemetry from the physical room. Yes. They specifically mention tracking ambient dew point, relative humidity, and facility airflow.
That correlation is the holy grail of facility management. A temperature spike on a silicon die means one thing if the facility air is perfectly dry and 65 degrees. It means something entirely different if the facility's relative humidity just spiked and the ambient dew point is approaching the temperature of the chilled water supply.
Because if the chilled water pipes get colder than the dew point of the room, they start sweating. Condensation forms on the outside of the pipes inside the server.
Exactly. And condensation is just as deadly as a physical leak.
How true.
By correlating the internal silicon temperature with the external facility dew point, the SEC can automatically raise the coolant supply temperature just enough to stay above the dew point. So it prevents condensation while still providing adequate cooling to the chips. It is a brilliant, dynamic balancing act.
Which brings us inevitably to the nightmare scenario. We have established how elegantly this system operates when the parameters are normal. We have perfectly balanced delta T's, we have predictive maintenance, we are avoiding condensation.
Right.
But I know what every single infrastructure engineer listening to this is waiting for. You're running thousands of gallons of pressurized water inches away from rows of NVIDIA H100s. A single server chassis is holding $750,000 worth of bare, unprotected silicon.
Yeah, it's nerve-wracking.
What happens when a fitting fails, a hose ruptures, or a cold plate cracks?
Yeah.
What happens when there's an actual physical water leak inside the rack?
It is the psychological barrier that has kept liquid cooling out of mainstream enterprise data centers for a decade. The fear of catastrophic, cascading failure, water, and high-voltage, high-frequency electronics are fundamentally incompatible.
So how does this architecture address the nightmare? Because they must have a plan.
They do.
The blueprints detail a highly structured framework called the zero-leak policy. And it is not just a single sensor hoping to catch a drip. They have designed a strict, dual-layered defense system. They fundamentally separate the incident response into two categories: external leaks and internal leaks.
That architectural delineation is crucial because the required response times and the blast radius of the failure are completely different depending on the leak type. Let's examine the external leaks first.
The documentation states that external leaks are managed by the CDU, the cooling distribution unit, at the bottom of the rack. They detail these specific external sensors, often described as rope sensors or conductive tape, that are physically wrapped around the main supply chains, the manifolds, and the primary hoses outside the server chassis.
So if a technician bumps a manifold with a crash cart, or a high-pressure quick disconnect fitting starts weeping fluid into the aisle, these conductive sensors immediately detect the moisture.
And when they do, the system doesn't just blindly kill the power to the entire rack, does it?
No, it doesn't.
The DevOps administrator has already configured an enforcement policy within the SuperCloud Composer software. The blueprints explicitly list 4 selectable actions for an external leak: no action, graceful shutdown, immediate shutdown, or a delayed shutdown.
This is where we see the software deeply respecting the economic reality of the workloads.
I can understand immediate shutdown, water detected, cut the power, save the hardware. But why would anyone select no action or a delayed shutdown when there is a known water leak near $1 million rack?
Because you are balancing the capital risk of the physical hardware against the operational risk of the data. Think about it. If you are a cloud provider and you are on day 28 of a 30-day training run for a massive large language model,
which costs millions of dollars in compute time, right?
exactly. If the system executes an immediate hard power cut to the entire rack because a hose in the aisle is dripping, you could corrupt the memory state, fail to write the model weights to non-volatile storage, and literally lose a month of multi-million-dollar computational work.
Just gone. Over a drip.
Yes. So the delayed shutdown policy, which the documentation specifically highlights for storage servers and LLM inference models, is a negotiated compromise. The administrator is effectively telling the SEC, I acknowledge there is a leak in the aisle, the hardware is at risk, but before you kill the power, give the operating system 60 seconds to flush its cache to the NVMe drives, commit the database transactions, and save the state of the neural network. You risk some water damage to a chassis to ensure you don't lose the intellectual property being generated by the silicon.
Okay, that makes perfect sense for an external leak. A drip in the aisle gives you a 60-second window. But what about the second layer? What happens if the leak is internal?
That's a different story.
Like, what if the microchannels inside the copper cold plate, the piece of metal bolted directly on top of the CPU? What if that seal fails and fluid leaks directly onto the motherboard?
That is a totally different threat profile, and the architectural response changes completely. There is absolutely no time for negotiation.
The blueprints state that internal leaks are not handled by the SEC software in Taiwan. They are handled directly, locally, by the BMC.
The baseboard management controller.
Yes. Let's pause here and really explain the BMC, because it is the unsung hero of this entire operation.
It really is. The BMC is essentially an entirely separate, tiny computer embedded directly onto the motherboard of the main server.
Okay.
It runs its own independent operating system, it has its own dedicated network port, and crucially, it operates completely out of band from the main CPUs. The main server can be powered off, crashed, or completely locked up, and the BMC will still be online, monitoring voltages, fan speeds, and temperatures.
And according to the zero-leak architecture, there is a humidity or moisture sensor positioned right at the cold plate, wired directly into that local BMC.
Right.
If that sensor detects fluid, the BMC does not send an alert to Taiwan and ask for permission. It does not check the user's delayed shutdown policy. It instantly triggers a physical relay to kill the power from the PDU.
It is a digital guillotine. If water is touching the silicon traces on the motherboard, a delayed shutdown is pointless. The electrical short will destroy the hardware before the operating system can even begin to save its state. The BMC cuts the high voltage instantly to prevent a thermal event or permanent silicon damage.
The internal documentation brings up this fascinating concept of a tug-of-war. Because if you think about it, both systems are monitoring the rack simultaneously.
Yeah, they are.
The overarching SEC software is polling the rack, and the localized DMC is monitoring the specific server. How do they avoid conflicting instructions in a crisis? Like, if the SEC policy is set to graceful shutdown, but the BMC detects an internal leak, who wins the tug-of-war?
The BMC must win. It requires ultimate, unquestionable authority in a localized physical crisis. It's all about the hierarchy of latency and proximity.
It reminds me of the human nervous system.
Oh, how so?
Like, if you accidentally place your hand on a red-hot stove, you don't wait for the nerve signal to travel all the way up your arm, into your brain, for your conscious mind to process the heat, decide on a graceful hand removal policy, and send a signal back down to your muscles.
No, absolutely not. Your spinal cord intercepts that pain signal and physically violently retracts your arm before your brain even knows you are burned. It is a localized, hardwired reflex designed to minimize tissue damage.
Exactly. The BMC is the spinal reflex of the AI factory. If there is water on the motherboard, the BMC forcefully retracts the power. The SEC in Taiwan is the brain. It finds out a few milliseconds later that the server went dark, and it handles the high-level response like migrating the workload to a different rack and alerting the maintenance team.
That is a flawless analogy. The clear delineation of responsibility, local hardware protection versus global workload management is exactly what makes the architecture robust. And what is incredible is that this layered safety philosophy extends all the way out of the server room and into the physical environment of the building itself.
Right. The documentation details a third safety layer, the cooling tower.
Yeah.
Because, all this heat that the fluid is absorbing from the silicon has to go somewhere.
Yeah, it doesn't just disappear.
It gets pumped outside the building to massive cooling towers that reject the thermal energy into the atmosphere.
And those towers are brutal industrial environments. They are exposed to weather, debris, and massive temperature fluctuations.
The blueprints detail that SCC is monitoring 30 distinct sensors just on the cooling tower layer alone. They are tracking ambient airspeed, fan RPMs, and the physical water level in the collection basin. And they highlight one highly specific vulnerability, the float sensor.
To understand why the float sensor is critical, you have to understand evaporation cooling. These towers reject heat by spraying the hot return water through the air, allowing a portion of it to evaporate, which massively cools the remaining fluid.
Okay.
Because you are constantly losing water to evaporation, the tower basin is continuously refilled via a high-pressure municipal city water line.
It's essentially a massive industrial version of the float valve in the tank of your toilet. As the water level drops, the float lowers, opening a valve to let city water in. When the tank is full, the float rises and shuts the valve.
Exactly. But if that mechanical float sensor scales over with minerals or jams in the open position, that high-pressure municipal water line will just keep running.
And the documentation points out the catastrophic consequence of that. If the tower overflows, that excess municipal water can actually flow backward through the plumbing trenches, breach the facility containment, and literally flood the data center from the outside in.
Which is why the SEC software monitors the basin level electronically. If the water level exceeds the mechanical float threshold, the software can remotely actuate an emergency shutoff valve on the city water main, preventing a localized mechanical failure outside from flooding millions of dollars of hardware inside.
It is breathtakingly comprehensive. We are protecting the microchannels on a silicon die from a single drop of condensation, and simultaneously protecting the entire campus from a municipal water flood, all managed through the exact same telemetry engine.
It's engineering at its finest.
It really is.
Yeah.
Okay. We have saved the servers from melting. We have saved them from drowning. We have established that the physical plumbing and the software telemetry of these liquid-cooled AI factories are resilient.
Yep, the physical layer is secure.
But now, this deep dive is going to pivot into the true end game of all this technology. Because keeping the servers alive is only half the battle. Now we have to look at how we keep the cloud providers from going bankrupt. We are moving from the physics of thermodynamics into the brutal economics of the global power grid.
This is where the narrative shifts from being an incredible IT achievement to a foundational shift in global infrastructure entirely. The power density of these liquid-cooled AI factories is so immense, we're talking tens or hundreds of megawatts for a single campus, that they fundamentally cannot be treated as traditional utility customers.
The internal documentation introduces this critical economic concept, locational marginal pricing, or LMP. And for anyone who just pays a flat rate for their home electricity, LMP is a completely different universe.
Oh, completely.
The documentation defines LMP as the total financial cost to deliver 1 megawatt of power to a very specific node on the electrical grid at a highly specific moment in time.
Right. And to understand why LMP is so dynamic, you really have to discard the idea that the electrical grid is a giant battery or an infinite pool of energy. It is a highly constrained physical network of spinning turbines, high-voltage transmission lines, and step-down substations.
And because we don't have grid-scale storage, every electron of electricity has to be consumed the exact millisecond it is generated.
Exactly.
The grid operators, the text specifically names CAISO in California, PJM in the Northeast, and ERCOT in Texas. They are fighting a second-by-second war to keep generation perfectly balanced with consumption. And they use the LMP pricing mechanism to financially incentivize that balance.
It's all about financial incentives.
The blueprints break the LMP calculation down into a 4-part formula. And I want to dig into these mechanisms because they dictate everything about how these AI factories operate. The formula is marginal energy cost plus marginal congestion cost plus marginal loss cost plus a greenhouse gas carbon compliance cost.
Right. Let's break down how these physical realities translate into financial penalties. First, the marginal energy cost.
What's that?
This is the baseline. It is the raw economic cost to generate 1 additional megawatt of electricity anywhere on the system, assuming the transmission lines are completely empty and have infinite capacity. It represents the cost of the natural gas being burned or the wind spinning the turbine at that exact moment.
Okay, so it's the pure commodity price. But the grid doesn't have infinite capacity, which brings us to the second and arguably most volatile variable, marginal congestion cost.
Congestion, yeah.
The documentation defines this as the premium incurred when the transmission lines between the cheap power plant and the data center are physically maxed out. But wait, how does a power line actually get maxed out? It's just metal wire.
It comes down to thermal limits. When you push high voltage across a transmission line, the electrical resistance of the metal generates heat. If you push too much power across the line, the physical metal wire gets so hot that it begins to thermally expand and sag.
Sag. Like droop down.
Yes, physically sag. If it sags too low, it can arc to trees or the ground, causing a massive short circuit and a cascading blackout.
Wow. Okay, so the grid operator literally cannot push more cheap power down that line no matter how much you want it.
Exactly. So if your data center in a crowded city needs more power, but the lines bringing cheap hydroelectric power from the mountains are at their thermal limit, the grid operator is forced to spin up a highly expensive, inefficient natural gas peaker plant located right next to the city to meet your demand.
Huh.
The congestion cost is the massive financial penalty you pay for forcing the grid to use the expensive local power plant instead of the cheap, distant one.
That makes total sense. You are paying for the physical traffic jam. Then the third variable is the marginal loss cost. The documentation notes this is the cost associated with the energy that is physically lost as heat as electricity travels over long distances.
Yes. This is basic electrical engineering I²R losses. When you transmit power hundreds of miles, a percentage of that electrical energy simply dissipates into the atmosphere as heat.
Just poof, gone.
Just gone. Furthermore, you lose efficiency every time you run the power through a transformer to step the voltage up for transmission and step it back down for distribution. If the generator produces 100 megawatts, but the resistance and transformers eat 5 megawatts along the way, the data center only receives 95 megawatts.
So marginal loss cost ensures the consumer pays for the 5 megawatts that vanished into thin air.
Precisely.
And the final piece of the formula is the GHG, the greenhouse gas carbon compliance cost. This is the regulatory cost imposed on carbon-emitting generation sources, factored directly into the wholesale price.
Right.
So you add up all the physical realities, the raw energy, the thermal congestion of the wires, the resistance losses, and the carbon penalties. That gives you the real-time LMP. And because human behavior is erratic and weather is unpredictable, this LMP value fluctuates wildly minute by minute.
The geographical disparity of LMP is staggering. The documentation provides two extreme pricing scenarios to illustrate the environment these data centers are operating in.
Okay, what are they?
First, look at a heavily constrained urban environment during a summer heat wave. You have millions of air conditioners running. The localized demand is immense, but the transmission corridors into the city are completely congested.
So the lines are sagging.
Yes. The LMP in that specific urban node skyrockets to astronomical levels. The grid operator is using that massive price spike as a financial weapon, incentivizing any available generator to spin up, and screaming at large industrial consumers to shut down.
Shut down or pay the ultimate price.
Exactly. But then the documentation contrasts that urban nightmare with a completely different reality. Remote areas with abundant renewable generation. Picture a massive wind farm in West Texas, or a massive solar array in the desert.
Right. On a perfectly sunny, highly windy day in the spring, those renewables are generating maximum power. But it's 65 degrees outside. Nobody's running air conditioning. The localized demand is near zero.
And more importantly, the transmission lines leading out of that remote area are too small to carry all that power to the cities.
So you have a massive oversupply of power trapped in a localized node.
Exactly. And this creates a severe physical danger to the grid. If supply massively outpaces demand, the alternating current frequency of the grid begins to spike above 60 hertz.
I think it's bad.
Very bad. If the frequency gets too high, it will literally destroy transformers and industrial motors connected to the grid.
The grid must remain balanced, which leads to one of the most fascinating economic quirks in the entire documentation: negative LMPs.
Yes, negative LMPs.
The grid operator is so desperate to maintain the AC frequency that the locational marginal price literally drops below zero. The grid will financially pay large industrial consumers to absorb that excess electricity.
They will pay the data center to run its supercomputers. It is a phenomenal economic dynamic.
Just please do more math. Here is some money.
Exactly. And this extreme volatility, from massive price spikes in cities to negative pricing at wind farms, has forced a major shift in federal energy regulation.
Right. The documentation cites a highly specific regulatory unlock. The Federal Energy Regulatory Commission, or FERC, Section 206 order, and they quote FERC Chairman Laura V. Sweat directly regarding this framework.
And just to be clear, we should frame this objectively.
Yes, just to be absolutely clear for our listener, we are analyzing this strictly through the lens of regulatory mechanics that enable technology. The quote from Chairman Sweat states, "We are setting the stage for a resilient, reliable, and forward-thinking grid that empowers communities and safeguards consumers by transforming the way large energy users access the grid." She emphasizes protecting existing utility deals while simultaneously unlocking new market opportunities for technological advancement.
What FRC Section 206 functionally achieves is dismantling the regulatory barriers that previously prevented massive industrial loads, like AI data centers, from acting as dynamic market participants. It creates the legal and economic framework for them to react to those wild LMP fluctuations.
So, as a consumer, if I am a developer renting cloud infrastructure to train my AI models, why do I care about wholesale LMP formulas and FERC regulatory orders? Why does this matter to the end user?
It matters immensely to the cost of your compute. Traditionally, a data center operated on a static power purchase agreement. They negotiated a flat rate of, say, 7 cents per kilowatt hour, and they just ran their servers 24 hours a day, 7 days a week, completely blind to the grid stress. But the documentation refers to this new generation of operators as neocloud providers. These neoclouds recognize that with AI workloads pulling tens of megawatts, a flat-rate contract is economically inefficient. They are emboldened by FE-SURE 206 to play the dynamic LMP market to maximize their margins.
Because if a neocloud provider can physically avoid running your massive AI training job during the 3 hours a day when urban congestion drives the LMP to peak penalty pricing, and instead dynamically shift that processing power to the overnight hours when wind farms are causing negative LMPs, their profit margins on that compute time expand exponentially.
Exactly. They are no longer just selling technology infrastructure. They are conducting high-frequency energy arbitrage. They are an energy trading firm that happens to process data.
That is just wild to think about. Which brings us to the ultimate synthesis of this entire deep dive. We have explored the microscopic fluid dynamics of the liquid cooling. We have analyzed the global telemetry of the SuperCloud Composer software, and we have decoded the macroeconomics of the LMP power grid.
The three pillars.
Exactly. So what happens when you wire all three of those disciplines together? What happens when the liquid-cooled AI infrastructure directly interfaces with the dynamic energy grid?
This is the convergence. This is the birth of grid-aware compute.
The documentation details a specific toolset built to execute this, the Power Grid Manager. And it's a direct collaboration between Supermicro, Ventus Energy, and C-Power. Their explicit goal is to unify the management of the data center's internal cooling and compute assets with the external realities of the power grid. They are taking the AI factory and upgrading it into what the industry calls a virtual power plant, or a flexible load entity.
Let's define that term. A traditional data center is a rigid, inflexible load. It turns on, it draws 50 megawatts, and it refuses to yield even if the grid is on the verge of a rolling blackout.
Right, it's just a brick.
A very power-hungry brick. A flexible load entity, however, is fundamentally malleable. It has the physical capability and the software intelligence to shape its massive power consumption in real time, responding instantly to the external economic or physical signals from the grid operator. It acts as a massive, multi-megawatt shock absorber for the electrical grid.
And the mechanism they use to achieve this flexibility is deeply fascinating. The blueprints call it GPU flexing.
GPU flexing, yes.
And I want to emphasize this because the documentation is incredibly adamant about what GPU flexing is not. When a grid emergency happens or prices spike, they do not evacuate the AI workloads to a different data center.
That is a vital distinction to make. In the early days of cloud computing, the theory was follow the moon. If power got expensive in California during the day, you would dynamically migrate the virtual machines to a server cluster in Texas, where it was night and power was cheap.
But the documentation makes it clear that workload migration is totally unviable for modern AI. Why?
Right. Latency and capital inefficiency. If you are training a massive large language model, you have terabytes of model weights loaded directly into the high bandwidth memory of the GPUs. You cannot simply package that memory state and instantly transmit it over a fiber optic line to Texas. The network latency would stall the training run for hours.
Right, it's just too much data to move quickly.
Exactly. And furthermore, from an economic standpoint, if you are migrating workloads from California to Texas, it implies you have a massive identical cluster of H100 GPUs sitting completely idle in Texas, just waiting for California power prices to spike.
Yeah.
You are paying for hundreds of millions of dollars of redundant capital expenditure that sits unused 90% of the time. It destroys your profit margins.
So instead of moving the math, GPU flexing just slows the math down in place.
Exactly.
During a grid demand event, the Power Grid Manager software receives the high LMP price signal. It communicates with the SEC appliance, which routes a command directly down to that localized BMC, the spinal reflex we talked about earlier.
The spinal reflex, right.
The BMC issues a low-level hardware command to the GPUs, forcing them to transition to a lower P state or performance state. It dynamically drops their clock frequency and their voltage.
And because of the nonlinear relationship between voltage, frequency, and power draw, dropping the clock speed of a GPU by 20% might actually reduce its electrical power consumption by 40% or 50%. The hardware is still processing the AI model, the memory state remains perfectly intact, but the server is suddenly drawing half the power.
The presenter in the documentation, Kevin Culp, used an analogy that perfectly captures the mechanics of this. He said, it's like turning down a water spigot to a drizzle. You don't disconnect the hose, you just turn the valve to a 3/4 turn, and the flow of water, or in this case, the flow of computations and power slows down.
Oh, I love that analogy.
Yeah. And when the Power Grid Manager receives a signal from the curtailment service provider that the grid frequency has stabilized or the LMP price has dropped back to baseline, the software opens the spigot back up, the BMC restores the maximum voltage, and the GPUs instantly ramp back to peak performance.
It is an incredibly elegant, purely software-defined approach. It requires no new hardware inventions, no massive batteries, and no redundant data centers. And importantly, it operates agnostically across the entire silicon ecosystem. Whether the factory is running NVIDIA, AMD, or Intel accelerators, the BMC can execute the dynamic frequency scaling.
Okay, I have to push back on this on behalf of the developer who is paying the NeoCloud for this compute time.
Okay, go ahead.
If I am renting a cluster of multi-million-dollar GPUs and my complex inference model suddenly takes twice as long to execute because the NeoCloud provider decided to throttle the hardware to save themselves money on their electric bill, isn't that a fundamentally terrible user experience? Why would anyone accept a data center slowing down their math? Is this actually better for the end user?
It is a totally valid concern, but you have to view it through the lens of total economic cost. If the NeoCloud provider is forced to buy redundant hardware in Texas, or if they are forced to absorb those astronomical $5,000 per megawatt-hour LMP penalty spikes during a heat wave, they are going to pass those costs directly onto you, the developer. The hourly rental rate for that GPU cluster will be astronomically high.
Ah, so they are trading time for cost.
Exactly. By utilizing GPU flexing to ruthlessly optimize their wholesale power costs, the NeoCloud can offer the compute time at a significantly lower, highly competitive baseline rate.
Makes sense.
And you have to look at the nature of the workloads. AI training runs take weeks or months to complete. They are not strictly time-sensitive down to the millisecond, the way a high-frequency trading algorithm is. If a developer is told that their training run will take 31 days instead of 30 days, because the system will automatically throttle during afternoon grid peaks, but the total compute bill will be 30% cheaper, developers will aggressively opt into that SLA.
Oh, absolutely. It is a massive margin victory for the cloud provider and a cost victory for the developer. But zoom out from the data center for a moment. This capability is an absolute godsend for the stability of the electrical grid itself.
A total game changer.
If a severe heat wave settles over California and millions of air conditioners are pushing the grid to the absolute brink of a catastrophic blackout, the grid operator can send an automated dispatch signal. Within seconds, these massive AI factories instantly drop their consumption by 40%. They shed tens of megawatts of load simultaneously.
Which is exactly why they are classified as virtual power plants. To the grid operator managing the delicate 60 Hz AC frequency, a data center instantly shedding 50 megawatts of load provides the exact same physical stabilizing effect as a natural gas peaker plant instantly spinning up and adding 50 megawatts of new generation. A megawatt saved is a megawatt earned.
To prove that this isn't just theoretical white paper architecture, the documentation details live demonstrations that were executed at the ISC 2026 venue in Hamburg, Germany.
Right, the dual demo.
They set up two entirely distinct, globally separated converged AI factories to prove that this grid-aware compute functions across vastly different regulatory and physical grid environments. One setup was simulating operations in San Jose, California, and the other was simulating operations in Den Bosch, Holland.
The contrast between those two demonstrations perfectly illustrates the sheer adaptability of the Power Grid Manager software, because managing power in California is a fundamentally different discipline than managing power in the European Union.
Right. The San Jose demonstration operates within the fiercely dynamic, market-driven North American grid.
Yeah.
The dashboard for the San Jose facility is intensely focused on the LMT variables we unpacked earlier. It is integrated with highly precise e-gauge meters, tracking the marginal energy cost, the localized congestion, and the line loss in real time. The San Jose AI Factory is acting autonomously. The software's algorithms are constantly evaluating the LMP price and deciding to flex the GPUs based purely on localized financial logic.
It is a market-reactive system. If the price gets too high, it throttles to protect margins. But the Den Bosch setup operates under a completely different regulatory philosophy.
Yes, the documentation highlights how the EU grid operates. They don't use localized node pricing in the same volatile way. The EU utilizes massive zone boundaries called BZNs, and they operate on auction-based nodal pricing that shares power across national borders.
Because of that cross-border sharing and the heavy integration of offshore wind, the primary threat to the EU grid isn't just localized price spikes, it is systemic frequency instability.
So the dashboard for the Den Bosch AI Factory isn't aggressively tracking congestion costs. Instead, it is structurally integrated with the European curtailment service providers.
Right.
The Den Bosch facility throttles its GPUs, not because an internal algorithm decided power was too expensive, but because a central grid operator sent a direct automated emergency curtailment signal demanding a load reduction to prevent a regional blackout.
The catalyst for the throttling is completely different. A financial market price in California versus a direct regulatory emergency signal in Europe. But the Power Grid Manager software ingests both realities elegantly. It translates either signal into the exact same mechanical outcome, instructing the BMC to execute dynamic frequency scaling on the liquid-cooled GPUs.
And the fact that they are managing all of this simultaneously, I mean, think about it. They are pulling complex API data from global grid operators. They are actively monitoring the precise delta T temperatures of the microscopic liquid cooling loops. They are predicting hardware failures, and they are dynamically adjusting the clock speeds of thousands of GPUs. And they're doing it all from a single, unified architectural framework.
It's unbelievable.
It's a breathtaking convergence of disciplines. You have deep-level thermodynamics, enterprise software engineering, and macroeconomic energy policy all functioning together as a single breathing organism.
It is the only pathway forward. If we are going to deploy artificial intelligence at the massive multi-gigawatt scale that the global economy is demanding, we can no longer treat data centers as isolated, parasitic silos that just plug into the wall and consume. They have to become deeply integrated symbiotic organs within the larger body of our global infrastructure.
It really is a profound journey we've taken today. We started this deep dive looking at the microphysics of a tiny drop of water being pumped across the copper fins of an AMD processor in a single, incredibly dense server rack. And tracing the logic of that heat management upward, layer by layer, we ended up analyzing macro-level European grid energy auctions and the deployment of virtual power plants to stabilize the electrical grid.
It's all connected.
The sheer scale of the engineering required to make modern AI function is completely invisible to almost everyone who uses it. But it is fundamentally, quietly rewiring how our physical world operates.
And as the demonstrations from 2026 clearly validate, this is no longer theoretical architecture. The convergence of liquid cooling and grid-aware compute is the new baseline reality of high-performance infrastructure.
It has been an incredibly enlightening deep dive into these materials. And as always, I want to leave you, our listener, with a final provocative thought to mull over, something that builds on the incredible mechanisms we have explored today.
Absolutely.
If these massive AI factories are now fully capable of acting as virtual power plants, if they can intelligently flex and throttle their multi-gigawatt power consumption instantly based on real-time grid telemetry, could the data centers of the future actually become the primary stabilizing force for the entire global renewable energy transition?
That's the million-dollar question.
Right. As our society relies more and more on highly unpredictable power sources, like the wind blowing or the sun shining, grid operators are desperate for massive shock absorbers to balance the supply and demand. What if the very supercomputers that are training the next generation of artificial intelligence are also the exact mechanisms keeping the lights on in our cities when the wind stops blowing?
That's a fascinating thought.
The rigid line between a technology company and a public utility company might just be disappearing entirely.
I think you're right.
Well, thank you so much for joining us for this deep dive into the source material. We will see you next time.